So let's review from lab a couple weeks ago. And let's name the white blood cells.
Lymphocytes, monocytes, basophils, neutrophils.
I'll do them in the order I remember. Never let monkeys, right? Lymphocytes, monkeys, monocytes, eat bananas. One year I just wrote bananas up there, no one caught it. Right, but remember, never let monkeys eat bananas. Never neutrophils, lymphocytes, monocytes, eosinophils, basophils. So these are running through your body, basically, in the plasma, and they'll just eat whatever they come up against. So let's review from lab what they eat. What did neutrophils attack? Bacteria. So if you're a bacteria, doesn't matter which one, and a neutrophil hits you, it should eat the bacteria, all things being equal. You're actually going to cross off lymphocyte, because those are not part of the non-specific events. We'll talk about them later. They're specific. So we'll leave them off the list. Let's go to monocytes. What do monocytes eat? Everything. Anything and everything. So it doesn't matter, I will eat you. Eosinophil. Wormy thingies, parasite, wormy thingies. Honeymoon in Guatemala. All right.
Yay.
Basophils. They produce histamines. So they don't eat histamines, they produce histamines. So we'll talk about them a little later too. So the three main ones would be your neutrophils, your monocytes, and the eosinophils. They're actually eating whatever they bump into. So on the farm, we call this step the white blood cell patrol. When you're in the military and you're on patrol, what are you supposed to be doing? Watching and killing whatever you're supposed to guard and defend. So you're patrolling the body, non-specifically eating whatever comes your way. That's level 3. Now let's say this doesn't work, or doesn't work well enough. What's level 4 going to be? DEFCON 4. Anyone guess what DEFCON 4 is?
Specific.
All right, let's do forward. Adaptive specific immunity. Okay, so let's look at these words. We have adaptive and specific. In English, what does adaptive mean?
To be adaptive to your environment.
Yes, and in English we mean learn. So this level can learn what to do. What does specific mean?
They target a certain thing.
Target, right. So in English, you are learning a target and how to kill it. You're being trained to kill something, yes.
Is this where your food allergies come from?
Part of this, yes. Yes. So, well, tolerance, allergies, and immunity are all in this category.
So adaptive is kind of like a vaccination, kind of?
Yes, because you're teaching it. So we're going to go over here and do more DEFCON 4 here. So, in your specific adaptive immunity, there are 2 branches that you have to learn. We're going to do both branches tonight. In my country. So you will hear people talk about B cells and T cells. They mean specific adaptive immunity. And then if we add the last word to both of them, they are both types of lymphocytes. I'm going to write poorly in there. So lymphocytes are the B's and T cells. They are part of the specific defense, or innate adaptive, whatever. Right, so we're going to learn both B's and T's. So to learn B's and T's, we first have to figure out why they're named that, which seems so silly. What is B and T? Okay, hey, femur is always the answer, right?
Yes.
Femur. So why is there a femur on here? What's that got to do with any of this stuff?
Bone marrow.
Bone marrow. We make all our blood cells from bone marrow, right? So in English, here are my bone marrow, and then here are my lymphocytes, but they're neither yet. Let's focus on this top one. The top one is going to go somewhere. Where is he going? To my thymus gland. And then we end up here. Where is here? Last name. Lymph node. So lymphocyte. So hey, the yellow one's a T cell. So guess what we got? T?
Thymus.
Thymus gland. So the reason we're called a T is we mature in the thymus. That is actually where they got the T. Thymosin-induced lymphocytes. So a T cell is made in the bone marrow, goes to your thymus, and ends up in the lymph system. Where does the B cell mature? Let's find out.
In bone marrow, in blood.
Yeah, we don't know, so we just, well, let's go B, why not? So it's made in your bone, ends up in the lymph system, but does not go to the thymus. So we just call it B. That's the only difference really in the naming is the thymus step of the T. But they're both lymphocytes, they're both made the same place, they both go to the same place, they essentially do the same job. Make sense?
Mm-hmm.
So B's and T's are basically the same kind of cell. They're both lymphocytes. Make sense? We don't, they used to say that it was matured in the bone, but they're coming out with data that says, well, maybe, maybe not, we just don't know. Which is probably more truthful than anything.
Okay,
So they're
now you're talking about where they mature.
right, they're mature before they get to the lymph node. That's the answer. Make sense on B's and T's?
Yep.
Okay, so we understand the naming and where they come from. The big idea you have to understand is this picture. This will haunt you a lot today. So let's go back to this guy. Remember that word?
The antigens.
Remind me what an antigen was or where it was? Protein on the surface of a cell, right? So this thing has antigens, proteins, markers, whatever you want to call it on the surface. It's like antigen, right? Okay. Look at this thing. This is a body cell. Where is that in your body?
All over
All over the place. Any body cell, pick a cell.
your skin cell.
Sure, why not? So, is that an antigen that you see poking out of it?
Yes.
Say yes. That is also an antigen. So any shape on the surface of a cell is an antigen. This one has a name called your MHC. So over there, we're going to make a list of this MHC and figure out what in the world it's doing. That's an important thing to know. So, MHC antigen. You also see it called a protein. They're synonymous. I don't care what you call it. Does anyone know why my body cell has that?
To protect your body.
Kind of, but more specific reason.
No lymphocytes, but it's okay.
So say I'm part of the body.
To protect
then-
the body.
Indeed. Very good. So the MHC antigen is what we call the self-antigen, meaning me. So now, why would you need to mark every body cell with you?
So it doesn't attack you.
Very good. So for this to work out, I have to know friend from foe. So this body cell is me. What do you think we call the antigen on little Mr. Foreign Microbe?
Not me.
Not me. How do you say not me in doctor speak? Non-self. Anti-me would almost be good, but. So to understand your B's and T's, you have to understand this concept of self and non-self. So anything that's my cell should be marked me, and everything that's not my cell should be marked not me, or have a different antigen. Make sense? Okay. If you understand that relationship between self and non-self, then you're going to have to stare at this picture a while, figure out what in the world's going on there. Take a look at that and tell me what you see.
It looks like it's memory, like it's memorizing,
Possibly.
Being
processing.
processed.
Yeah, it says process, I did that.
It's making antibodies for the bacteria that it's.
Possibly. So let's see if we can figure out in English what's going on here.
The
Is it
shape.
training?
There's something with the shape too.
Yes, indeed. So let's look at these. Who is this guy again?
It's bacteria.
Antigen.
That's bacteria, the pathogen or non-self, right? The non-self entered, what was this thing?
The mast cell.
Body cell, some by mine. So what's happening there?
It's breaking it up.
Breaking it up. So I'm eating, destroying lysosomes. Remember the lysosomes from last week, right? All that concept. So I'm breaking up the pathogen. Then explain this.
You're telling yourself that you're not yourself and to come eat me.
No, it's like covering
Actually,
the
yes,
receptor.
believe it or not, that's a very strange way to say it. But yes, that works.
You're
So,
saying I'm a bad cell, come eat me.
yes, I'm taking the non-self antigen and placing it on the self antigen. Why would you want to put the non-self antigen from what you just ate on the surface of your own antigens?
So that your cells can learn.
That's right. So I can learn what you just did. Remember, this is adaptive. So what the cell is doing is presenting the foreign antigen, the non-self, for the rest of the body to see it. And Why would you want the rest of the body to see it? So that the body can learn
And
that you
attack
just got
us.
infected, you just got invaded. Yes?
Why don't the other cells latch on to the non-self antigen and just destroy the whole cell?
They actually will. This cell will give its life for the cause. Okay? But not yet. Right? So this is probably politically incorrect, but so am I. In science, we'd call this a redneck cell. Right? What do you do after you shoot the deer? What do you do with its head?
You mount it.
You mount it. Hello. I just shot me a deer. Look, Bob, what I killed. But why you put the deer on your fireplace is to tell everyone that they can learn what a good hunter you are, right? This is the concept here. This cell's warning the body that I just ate something. Y'all look at this. Right. So that's actually the most important 3 steps of your life is right here. So we're going to go through these steps of this trophy announcement. So here we go.
Is it essentially saying, look at my poop?
Yes. Basically, look at my deer. Yeah.
I have a question.
Yes.
So is that just a process, the antigen presenting cell? Is that a process, or can we say that that's the cell?
It's the cell doing a process, so it's both.
Okay.
So let's go through step by step what this picture is showing you, right? So pathogen enters the body. How in the world did it get in?
You ate it.
Through all those things, I ate it, broke
Your
through my barriers,
nose.
inflammation, all that stuff you learned last week. So my pathogen got in. The pathogen is eaten by a white blood cell. That list you just erased, right? The white blood cells would patrol and see the pathogen like that and eat it. So if that's a bacteria, that'd be a neutrophil eating it, or a macrophage.
So
Yes?
is that cell then in the picture a white blood cell?
It's supposed to be. It doesn't look like one. That would be one representative of it. Now we get to step 3. The white blood cell presents the non-self antigen on the MHC. Remind me again what the MHC was?
That's yourself.
That's me, right? The non-self is not me. So I'm sticking not me on me. That's even English, right? So I'd look like that. So we call this antigen presentation, literally, or APC, an antigen presenting cell, or presentation of antigens. Lots of words for this step. But you're trying to announce to the body that I just ate something, look at me. Right? Make sense? This is antigen presentation. Well, why? Why are you presenting it again?
So the other cells can learn.
Other cells can learn. So we need to have someone look at this and learn something. So we're going to do step number 4 now. The self and non-self, in other words, the APC, is read. I'm using that in quotes, right? Cells don't read. You get the idea. It's looked at by a cell. That cell is called a helper T cell. You're going to underline that one in 3 colors, because it's going to come back to haunt you a lot. So once I do my APC step, another cell called a helper T cell is going to look at it. So let me show you a static picture of that. Then I'll show you an animation of that. This is more of a booky picture. Let's see if we can figure out what you have here. So on the left, virus. Is that self or non-self? I hope that's non-self, otherwise you're a virus, right? So here's my virus. It gets into, this happens to be macrophage, which is a type of monocyte. It could be neutrophil, it doesn't matter. And here's my white blood cell. He eats the virus, or it enters. We chop it up with our lysosome. And then notice what we did. We stuck it on the trophy zone. We put it on the MHC to announce to the immune system that's there. Here is my helper T cell. Notice what it's doing. It's reading, complementary binding, analyzing, making love. Okay. All right. So we're analyzing that shape. So the helper T cell looks at it, recognizes it, whatever we want. Then notice there's an arrow coming down for my helper T cell. So now the helper T cell is going to do something. Let's see what the wording is way down here. The word I want is that. proliferation. So step number, we're on 5? All right, so step number 5. After you, here are my lights. Once the helper T cell has read that selfie non-self stuff, then you go to step number 5. So the helper T cell orders proliferation. Proliferation. Okay, so let's first figure out what the word proliferation means. What does that mean in English?
Reproduce.
Reproduce. So I'm going to order proliferation of B cells and T cells. So the helper T cell is going to tell the other immune cells to reproduce. And why would you want to reproduce other cells?
Get rid of the virus.
Because you're going to have a war, right? You want troops to fight the infection. So you're going to order the rest of the immune system to come on board and proliferate, is the fancy word. Makes sense? So we just announced our trophy, so the helper T cell will order the other troops to do their job. Make sense? So tell me in the military, who do you call the people that give orders?
Drill sergeants.
Drill sergeants, officers, generals. So this is like the officer team of the military. So you can't do anything in the military without orders. So you have to tell the officers that you're doing something so they can give the orders to the rest of the army. That's the logic of this APC step. Make sense? Okay, so what we're going to do now is there's a different pathway for the B's and the T's. So we're going to start first with the B cell system. Go over here. And then we'll come back and do the T cell system. But what we've just done is got the T cell to be activated and start giving orders. Okay? So let me show you an animation before we go much further. It's courtesy of your Rafael.
Activation of the immune response typically begins when a pathogen enters the body. Macrophages that encounter the pathogen ingest, process, and display the antigen fragments on their cell surfaces.
So that's that antigen presentation. I have to show my trophy if the body wants to learn what's going on.
Macrophages with antigen fragments displayed on their surfaces are called antigen-presenting
Or
cells.
APCs.
An antigen-presenting macrophage interacts with a T helper cell that can recognize the same antigen.
So here's that general officer cell, helper T cell. It comes in and it's reading, quote, however you want to phrase it, that self and non-self distinction. So it would know that you are no longer just you. Yes.
Does it have to be a specific T helper cell?
In theory, yes. So there would be one T helper cell for every possible self-non-self interaction. Okay. But we don't know because if you don't have that, you'd be dead anyway. So it's kind of self-fulfilling prophecy.
And the antigen presenting cell isn't always just a macrophage, right? Other cells do that as well.
Right. Macrophage is the most common one.
It's
but
just, it's like a title that another cell can
Right.
take on.
So any of your white blood cells can do that, macrophages can do that. Sometimes things like the Merkel cells, and those ones in your skin can do that. But generally it tends to be macrophage more than that.
Okay.
So okay, so I just did 1, 2, 3, and 4. Now I'm up to step 5.
During the interaction, the macrophage releases a chemical alarm signal called interleukin-1, which stimulates the T helper cell to secrete interleukin-2.
Hey, that's a word you're supposed to know, Christie Pcc. So let's add interleukins. Right here, via interleukins. Okay, medical terminology, people. Interleukin literally means what?
In white blood cells?
Between white blood cells. So you're talking between the troops. So interleukin to a drunk Roman. Right? So all we're doing is we're activating our B's and T's via this interleukin chemistry to get them to come on board. So right now I'm going to start turning on my B's and T's.
Interleukin-2 causes the proliferation of certain cytotoxic T cells and B cells.
So what I'm doing now is I'm warning the rest of the army that we need to start learning how to kill. So we're going to do the B cell system first, and then we'll come back and do the T cell system. So let's do that. So I'm going to put them down for a second. I'm going to show you this picture here. All right, so these are B cells across the top, these big yellow blobs. You can tell I got excited in some class. Okay, what do you notice on the surface of these B cells? What do you remember these?
Antigen receptors.
Antigen receptors, or channels, or proteins, or active sites, or pick a word that you prefer. So remember, we have antigens on the surface of our bad guy. Yes?
Is there any reason why they're all two-pronged?
Just because I think they drew them that way.
Okay.
They're supposed to represent antibody, which is always two-pronged, but yeah, I don't think there's any reason it has to be. So here's my bad guy. He has antigen. Here are my B cells with antigen receptors. So what do you think antigen receptors and antigens are supposed to do?
Latch on the.
Okay, so look at the 3 B cells I have there. Will all of them grab the antigen?
No.
No. Why not?
They have the wrong receptors.
The shapes. Remember Biology 112 about the enzyme specificity, shape, and all that. So which of the B cells do you think would be the best grabbing the antigen?
One on the right.
This one?
Yeah.
Yay! He does. Look at that. He's going to grab onto a pathogen that has that antigen. So we're over here, we're going to start putting the steps that you're going to see once we've done that. The B cell system, over here. We're going to use leave lots of space. Okay, we're going to do the B cell system, which Saladin calls the humoral system. I don't care. Let's do B. That's fine. The first step, we'll use an A here. B cell attaches to an antigen on a pathogen. If you didn't like writing that antigen pathogen, you could have said also non-self, right? That's the same concept. So B cell is going to grab onto a pathogen floating around, right there. And what does my B cell do once it attaches the antigen on the pathogen?
That sprinkles out.
That's probably
What you're doing right now, absolutely nothing. It waits. It does nothing. Until what? Let's find out what's on the right side of the screen.
Well, that sprinkles out.
Sprinkle. Ooh, look there. Who's that on the right?
Helper T cell.
The helper T cell. So we're going to wait. Then on level C here, a helper T cell, the one that you activated over there, will now activate the B cell. I'm going to turn on my B cells. I'm going to activate my B cells.
And that's what the interleukin do?
Actually, that is actually with cytokines in this step.
Okay.
Another chemical called cytokine. Chemical terminology, people. Cyto means what?
Cell.
So kinetic means what?
Movement.
So you're going to tell the cell to move. Yes.
So the interleukin 2 is what proliferates
Yes.
the B cells,
Yes.
like you can be there at all.
Basically, yes.
And then it hangs out, and then it gets another signal, and then it gets activated.
Basically, that signal will actually be later than this one initially. So we grabbed on. Yes.
Why doesn't it just eat it? Does it hold it to feed to other ones?
Well, since I didn't build you, I don't know. But there is a logic to this.
Okay.
Because think of it in the army. If you kill the guy and don't tell anyone, what happens the next time you see more than one guy? They kill you and invade, right? So the logic is we do have to warn everybody that you're being invaded. And so if I kill, that's the logic that would be effective. So, but I didn't build it. I don't know. So, we attach, we wait, we get orders. And what are we going to do once we got those orders to activate? What do you think my B cell is going to do? What's the magic word? It's going to proliferate. Okay. And it's only this B cell will proliferate. Okay, if that word proliferate bothers you, in 112 you learned a synonym called clone. Can you tell me what it means to clone a cell? Duplicate, make copies, photocopies. So let's look at this picture. Here's my B cell that grabbed the bad guy. Here's my helper T cell giving orders to proliferate. And now look what I've made.
Babies.
I've made B cells. Look at their shape and tell me what you see. They're all the same because they're clones. They're all the same as what?
The original B cell.
The original B cell. And why would I think them all be the same as the first one?
They're the same side.
Because that means we'd all stick to the same antigen on this cell, right? It's that concept of specific. I'm going to stick to this shape on this cell. So we're going to clone copies of a cell that sticks to the invading non-self antigen. And they're all the same. We proliferated or cloned our B cells. Make sense?
What happens to the cell though that has stuck to the invader? Does it
Nothing,
die?
it'll just clone, it'll just do mitosis. But it's still holding the invader.
Okay. The invader doesn't
Well,
like
I'm sure he wants
phagocyze
to,
it, or?
I'm sure he wants to get out of there, but yeah, in theory, nothing yet. Yes.
What is the likelihood that all the people can be wrong? You try to screen all the cells and all actually work that way?
Right, so there are the interleukins that the B cells will release when they first grab and the APCs will release. So they do call them. But actually, T cells will actually go up and encircle every cell they see looking at these, believe it or not. That they can find. Yes, it's creepy to think about, but they do control. So let me show you another picture here. This is more booky, but this just shows what we just did. So here is my B cell, here are B cells. And here's my antigen invader, non-self antigen, pick a word you want. And just so happens, the middle one happens to stick with the right shape. So which one's going to clone? The middle one. So now we're making our clone. We're getting told by the helper T cell to clone our B cells. Now let's look what happens. We end up with two kinds of B cell babies.
Is that a mutation?
That's actually not. You actually want this, believe it or not. So step E over here. So some of the clones differentiate into different cells. So some of the clones are called plasma B cells. That doesn't mean blood plasma. They're found in plasma, but it doesn't mean they're plasma. All right? That's what you see on the left. These are plasma B cells. They're simply a type of this clone. And who's this over here? A memory B cell. So some of the clones become plasma, and some become memory B cells. So you have memory cells and you have plasma cells. They're both B cells. If you look at their shape, they're the same looking cell as above. They're supposed to be. All right, let's go through each one. The plasma cells, the ones that look like this, are going to do this. What are they doing there? What are those? Antibodies. So plasma B cells produce and make antibodies. All right. Remember when I said you had to understand that antibody-antigen thing? Remind me what antibodies did. They attach to antigens. So what I'm doing is I'm making proteins that will stick to antigens. Which antigen would it stick to? The one I found up here. So they make antibodies against this one here. So all the antibodies I made will be clones of the shape that stuck to the first one. So this is why it's specific. It only attacks that shape with those antibodies. Makes sense? So my antibodies will be secreted by my clones, and they will stick to the first shape I saw. So far, so good? All right. So big dude, why? What good is an antibody against an invader? It is. But why would you want to make antibodies at all? Very good. Let's look at this picture. This shows you what happens when you have antibodies that stick to antigens. So the Y's represent the antibodies. This thing is the bad guy or the antigen. So this says surround him. So your antibodies would stick around the outside of a cell. What do cells do if they're surrounded?
They can't do anything.
They can't do anything because I can't get into you, I can't really move. So you surround the guy. Remember in lab you did agglutination? That was the blood typing. What did your blood do when it agglutinated? They're clumpy. What do clumpy things infect you? No, because they can't get anywhere. So I'll make it so you're sticky so you can't move. This means I'll end up in your urine. So if you think about it, what you just did was you immobilized the pathogen. You're surrounded, you're stuck, you're now in P, but you're no longer able to move in me. So one of the goals of antibodies is to immobilize the pathogen. And there's several analogies that'll work. We also sometimes call this flypaper. Why do you put up flypaper? So the fly gets stuck in it. That's the logic here. So if you are stuck, you can't move around as a pathogen. Right? But then what do you do to the poor fly who's on the flypaper at some point?
Kill them.
You try to kill them, at least I do. Okay, so if you're stuck and can't move, look down here, what happens to you? What does phagocytosis mean in English? You're eaten by a white blood cell. If you can't run away, I can eat you, right? Or if you can't run away, I can do histamine release and get a whole lot of inflammation. Either way, you're dead because you can't escape from the immune system anymore. Make sense? So antibodies' job is to hold you down while someone else beats on you. That's basically what's going on. Right? Bar fight and psyop. The First World War, they had barbed wire up so you get caught in it so the machine gunners could fire at you more often because you couldn't get away. That's the logic here of the antibodies. I'm trapping you, the pathogen, the non-self, so the white blood cells can find you and kill you when they want to. Make sense? But wait, there's more. Because something else that'll happen is it'll fix the complement system. So antibodies immobilize and activate the complement system. Okay. Let's figure out what the heck complements are. So to understand complements, you have to look at this funny little picture and try to make sense of it. So, the Y's in blue. What are those? Those are the antibodies. So they're not doing anything, they just bind. This purple thing, that's the complement. And what does that look like right there?
The right shape or inside the cell?
That's a channel. So what would happen if I put holes in cells? What do? They leak and die. So eventually, your cell just bursts like a balloon. So the complement is a system of holes in cells. So the antibody isn't putting the hole in the cell. The antibody is telling the complement to put a hole in the cell. So now the cell leaks like a balloon. So when I get it all done, you're trapped in the wire, so I can eat you, and you get holes in you so you leak.
So I'm not quite understanding the complement.
Good, because I'm going to show you an animation that gives me an excuse. Right? Let's watch this animation. Here we go.
Complement consists of a group of serum proteins that activates inflammation, destroys cells, and participates in opsonization. Complement can be activated by a number of different foreign molecules.
So in English, okay, these are not cells. These are not white blood cells. These aren't T's and B's. These are simply proteins that are around in your blood. But they're inactive until they get told to do something. And when they get told to do something, they're going to start punching holes in cells and killing them. So the antibody's job is to signal, you kill this cell here. So what we're going to do is figure out how they do that. So watch this.
The complement proteins respond in a sequential manner, producing a cascade of reactions. The major components are C1 through C9, named in the order that they were discovered, not in the order in which they function.
Right.
The complement cascade can be activated by the classical pathway or by the alternative pathway.
So in English, there's more than one way to get this to work, but we're going to go through kind of the basics here. So here's my bad guy, my pathogen, my non-self-antigen. Here are the antibodies I just made over there in step E. The antibodies, when they bind, tell the complement system, I want you to kill this cell here. Punch a hole in this cell. All right, so what we're going to do is we're going to zip ahead here. There's all this chemistry you don't care about. To just about here. Here we go.
C5b reacts with other complement components, including C6, C7, C8, and C9, to form a membrane attack complex. This structure forms a hole in the cell membrane and causes cells to lyse.
So in English, once the antibody binds to the pathogen, that tells these proteins to put a hole in its membrane. The cell would leak and the cell would die. So you just killed the pathogen. But the antibodies didn't kill the pathogen. They simply told the complement which cell to kill. Right? So take home idea, antibodies don't kill anything. They either hold you down for someone else to kill or they tell the complement to kill. But they themselves just, that's the flypaper analogy. It just traps the pathogen. It doesn't actually kill the pathogen.
What's the inflammation for?
That's to get more white blood cells. So if we increase white blood cells, we get more response. Make sense?
So it's doing both of these things at the same
At
time.
the same time, you hope.
So the protein tells or the complement tells the antibody attached to the antigen to kill it.
By the way, right, the antibody tells the complement system to attack.
Okay.
Yes.
And the complement proteins are pathogens?
Yes. So let's go back to this picture. So we figure out where we're at so far. Remember we had that APC step, right? 1 through 5. So what we're going to do now is zip ahead to where we get the B cell to go. So here's my B cell.
When B cells become activated by T helper cells, they differentiate into plasma cells. These plasma cells become antibody-producing factories, flooding the bloodstream with antibodies that can bind to the antigen involved in this infection.
That's the concept of specificity. They are all alike, but they only stick to the antigen we saw at that very first little bit. If you look over here, see that little connection there? That's the antigen the B cell grabbed in A. Here comes the helper T cell from step 5 to say, I want you to kill that shape. And the B cell then makes antibodies that are exactly the same shape. So what should the antibodies do? Let's find out.
Antibodies bind to the antigens on the surfaces of the pathogens, marking them for destruction by macrophages.
So the Steven Seagal flick, Marked for Death. I don't know if admits to watching that. All right, so that's the concept. Once the antibodies have stuck to you, you can't escape. The white blood cells now know to eat you. So you're marked for death.
Some of the B cells do not turn into antibody factories, but instead become memory B cells that may survive for several decades.
So now we're going to fill in that chart. So what do memory cells do from this?
Protect you? Like help you learn your...
That's right. Memory cells
Yeah, faster response.
remember. What are they going to remember?
That specific
Pathogens.
That non-self antigen.
Oh, antigen.
And remember, it's adaptive. You're learning. So the memory cells are learning that this is who we kill. You like a military analogy, which I do. We're going to say these are your reserves. Why does the Army have reserves?
When they get overwhelmed.
In case you get attacked a second time, right? So we're going to use some of our troops to kill by making antibodies. Some of them we leave behind for the next round. So the next time an invader comes in, I already remember who to kill. I don't have to relearn. I've already been taught. Make sense? I'm not a raw recruit. I've already done basic. Make sense? So the memory cell is there to remember for next time. That's that adaptation. All right? Let me show you a picture of where this is going. So this is a graph showing antibody level, which would be B cells in there, versus when you're infected. So let's say you came home on the bus or whatever, some guy sneezed on you, blah, okay, here's time 0. How long did it take you to make antibodies against what the guy just sneezed on you? You don't even start anything until a week, and then you make all your antibodies by week 2. Why in the world did it take you 2 weeks to make antibodies?
Because you've never seen it before.
Never saw it before, I have to find it, APC, helper T. Remember, military is never efficient, right? It takes 2 weeks to get the bureaucracy of your immune system over to step E, right? Your bone marrow has to make more cells, all that stuff. So what happens to you in this 2-week period when you haven't done any immune response yet?
You get sick.
You get sick. The cold is running rampant through you because you have no immune system that's up to snuff yet, right? Let's say you live through it, hypothetically. Okay? Now, you get sneezed on a second time on the bus. On the same thing. What do you see happening on the graph now?
You remembered it.
I remembered it. So what do you see on the graph?
An extremely fast response.
extremely fast response. I went from 2 weeks to about 2 days, right? And how many antibodies did I make? More, about double. So the idea is stronger, faster, harder.
So that's
I
the
can
factor?
respond quicker and better because I've already taught myself who to kill and how to kill them. I remember it for next time, yes.
Will all subsequent exposures get that same secondary response? Or
Yes.
does it build?
Actually, it will. You'll get to a point, biologically, you can't make more, but every time you're exposed, you have more memory cells who can respond faster and harder. So each exposure, in theory, improves the response. Good point.
Is that why you get fever and get sick? It's the body responding stronger and stronger?
Yes, that's part of it. Yes.
Is that the idea of the flu shot?
That's exactly the idea of a flu shot for vaccine. So, since Portland people don't believe in vaccines because they're nuts, but anyway, I said that. All right. So let's go through it. So you go to get your kids vaccinated. What does the doctor inject into your child?
A deactivated virus.
An antigen of some kind, non-self, right, wherever it is. So what does the immune system do with non-self antigens?
It eats it.
All the way to E, right? So 2 weeks after you got your vaccine, your child does now have measles antibodies and measles reserve. That's not the point of the vaccine. The point of the vaccine is you have the memory cells for measles. So when you actually get the measles at the kindergarten, you kill measles before measles could have killed you. So you're creating memory ahead of time, is how a vaccine works. Right? Yes?
How do you inject someone with the non-self without them getting sick though?
That's the trick of it. So either you do what they call a dead virus, so you kill it by heating it, or you do attenuated, which is you breed it to be less toxic. Or in Europe they have what they call hapgen epitopes, which is you just take the antigen off, inject just the antigen. But what you're trying to do is something from the pathogen you inject to cause the immune system to respond. So epitopes are the easiest way, it's just the outside part.
But this doesn't work for everything. So
It would as long as everything didn't change its shape. Right, so measles doesn't change. So once I remember measles, I'll always remember measles. Flu changes, so I remember it this year, but it doesn't mean next year's flu I'll remember. Therefore, I have to get a new remembrance every time.
So that's why, I mean, they're saying that they almost have a universal flu shot because they found a secondary protein that they all share.
They all share, and it's less likely to mutate. Yes?
So I know it's really common to get sick a day or two after you get a vaccine. It happens to me. Why is that happening so quickly if it takes so, like what's going on there?
That's this whole thing here. So when you get the shot, you're going to have an APC eat it relatively quickly. This begins to turn on. So that's actually a normal response. That means the body's ramping up the immune response, trying to get to level E. So you may feel symptoms 1 or 2 days later. That's the inflammation in the white blood cells.
Well,
the actual antibody peak is 2 weeks later.
Well, and having a fever actually helps you fight it off. Like that's why
So
Tylenol is really bad because it's supposed to help you.
Makes sense? So in theory, once you have your 209th cold, you're done in your life. Because there are only 209 types of colds, you would remember all of them by your 209th one. I haven't hit that yet.
So I have a question about chickenpox. So chickenpox, like you get it, but then some say that if you get the vaccination, then you don't get it, and then you get
Shingles?
shingles.
Yes.
So tell me about that.
Sure. Like, my mom has shingles. Fantastic. All right.
Oh.
That started right. All right. So, you're diabetic who eats candy bars all the day.
Oh my
Hey,
God.
that's what happens. All right. So here's what happens with chicken pox. So you get chicken pox when you're a kid, like I did. Right? You get chicken pox, took 2 weeks to make antibodies, you have chicken pox, you're miserable, right? You then remember chicken pox. As long as my immune system can keep memory cells going, I'll never get chicken pox again. But guess what happens when you get older or my mother becomes a diabetic with a bad immune system and bad circulation? What happens to your immune response if you turn off your circulatory system? So then her memory cells can't get to the front. So the chicken pox re-enters her body. She can't get to this because her memory cells are not working well, so the chicken pox is back to here. Chicken pox now has 2 weeks to infect you a second time. So as long as your immune system is active and functioning, you won't get chicken pox twice.
So why is it shingles rather than chickenpox?
Because it hides in your nerves. So what it does, it uses the nerve as a way to get out of the central nervous system and attack the body. Because the white blood cells can't get into the nervous system.
Oh my goodness.
So therefore that's where it hides and comes out. But as long as your immune system's working, it should keep it in check.
Wow.
But when you become immunocompromised, like my mom, you get it a second time. Yes.
So you're a carrier your entire life?
Yes. You will always have varicella in your body somewhere. The goal is that your memory cells keep it from coming out. But once your immune system becomes compromised, it can get out without your immune system catching up. Yes.
Is that what they test for when they take a titer for the vaccine?
Basically, you're checking either antibodies or viral load. Antibodies is usually what they're checked for.
What about the super virus?
Which one?
Like
They're all going to kill you at some point.
Well, I mean, like in the hospitals, the MRSA.
They're resistant to antibiotics, so your immune system's fine. It's just that the stuff the doctor hands you won't work.
So you shouldn't take as much antibiotics, right?
Well, in theory, we've already crossed that bridge, right?
Yeah.
Antibiotics no longer work, but that's not because of this. This always works, right? The trick is you have to live through it to see the effect. So MRSA will kill you 50% of the time, so most of us won't get to here. If you live through MRSA, you'll be immune. The problem is you don't live through it. Yes?
So this long series of steps is for adaptive specific immunity? Yes. And then how does number 3 work, the innate non-specific defenses, the white blood cells? Is that steps 1 and 2 of this? Pathogens eaten by the white blood cells?
Yeah, that's basically how you got to step 1. So you had to eat it with a white blood cell to start this innate response. Yes.
So for like vaccines where they do like series where you have like maybe 5 that are in the series, is that just basically you're just kind of bringing it up to a level and then you're fine to go to another level?
That's right. So when I have a booster shot was to keep reminding the memory cells what the thing looked like. So you keep building memory with every booster shot. So you have a series, usually takes more than 1 shot to build an adequate level of reserves. That's the titer number. So this is worth the trivia, but the more common the pathogen, the better your memory is the first time because you're being re-exposed by everybody on the bus. Right? If it's something rare, then you have to boost it because otherwise your memory cells won't remember enough of it often enough to keep boosting. So in theory, you can't get it twice unless it's rare enough that you didn't see it more than once. But vaccines are to build immunity. Right? So get your kids vaccinated. It works really well. Yes?
Did you say that once you have a memory cell, how did you feel like you have it forever?
We believe it's forever. It's hard to prove that, but we believe it's forever.
Sorry to bring shingles up again,
Sure.
but it's also brought on by stress. So
Yes.
in cases of severe stress, are you then like immunocompromised?
Yes, you are.
Can't, and that's why you can't
In
respond.
fact, the group tonight did that. One of the stress hormones is cortisone, right? What did cortisone do to your inflammation and all that? Yeah, so the more stressed you get, the more likely that shuts off because if you get attacked by a bear, you don't need immunity. Right? So finals week, you'll all get sick. I do every finals week because of this. Once I get stressed, my immune response doesn't work. I got 2 weeks left and I just caught a flu. I put it on my calendar. March 14th.
What happens if you have chronic stress?
Then you're going to have a miserable life. Really. Stress will put you in the grave. Yeah.
So,
okay.
So boosters, it can like so somebody that just doesn't get a booster shot for something they need to do compared to somebody that just never had it at all. The person that just didn't get their booster probably has a better chance at defending than somebody that didn't.
Because any exposure would create any memory cell at all. So exposure and living through it is better than no exposure at all. That is living through it. But yeah, the more boosters you have, the better the tighter response.
So what happens with, like, you do it every 10 years or pertussis? So why, I mean, do your memory cells?
That's actually not for memory. It's an antitoxin. That's actually different. You actually don't make memory cells for the tetanus toxin. So therefore,
why do you have a 10-year, I mean, why does it?
In theory, it lasts longer, but they just tell you 10 years. So that's not actually against the tetanus bacteria. That's against the toxin it produces, which is a different ball of wax.
So,
this one remembers antigens.
Sorry, I'm just so interested in this. So
Yeah.
evolutionary wise, like our bodies are not really meant to be like, I don't know, forced to like be immune because like we get immune through our mother, right?
Not forever.
Well, not forever, like 6 weeks, 6 months or whatever.
6
but
weeks.
the thymus is there to help children get immune to things.
But it has to remember them.
Yeah.
That's the catch. So all you're doing in the vaccine is making the memory hit before the child has got the measles and mumps. That's the trick. So you're using the immune system's own reserves to force it on earlier. That's all. It's exactly the same procedure. But they have to be exposed to remember. That's what kills people, this exposure.
So, I'm not saying I would do this, but I'm just curious.
I'm a friend.
But when you talk about vaccinations, how you kill the bacteria by cooking it and then give it to somebody,
Yeah.
Well, could somebody like do that at home? I mean, do they just
Oh, wow.
like have someone spit this out in different petri dishes, grow the bacteria, cook it, and
Yeah, that's kind of.
Yeah. You can do that. I mean, there's nothing, it's just the devil's in the details, right? If you cook it too much, then it unravels and you lose the antigen. So the trick is you have to maintain the antigenic integrity without having the thing kill you. Right? Or you can just have children. Don't bring home antigens all the time. Yes, sure.
Well, why do they make them in the vaccines and eggs because they proliferate inside? I mean, why
Yeah.
do they? Okay.
It's easy, that's
So
the
they would
protocol.
use the stuff inside the eggs.
Yeah. So we get this idea of memory cells. Let's go back to our animation. So now we just did E, so let's finish watching this.
Because of these memory B cells, the secondary immune response to a future infection by the same pathogen is swifter and stronger. This powerful secondary immune response is what gives immunity to some diseases after you have had them once or after you have been vaccinated.
Your mom told you if you live through it, you will never get it again. That's the logic of the memory cells. So if I have it, I can remember it and I'll kill it before it kills me. You hope.
Is that a fairly universal thing, or are there some pathogens that are just so virulent that your body couldn't respond in time, even if you had antigens and memory?
I mean, you have two types of virulence. You have the ones that are really fast. If the virus or bacteria can go in that quicker than that 3 days when your memory cells will kick in, like for example, the flesh-eating staph will eat you in a day.
Yeah.
Well, that's faster than your immune system response. You're dead anyway. If it can change repeatedly, such as the flu, then you'll never get memory because it's always changing, so you have to relearn every round. And so things that mutate quickly will outwit the immune system. Things that are quicker than that week or 2 weeks or 3 days will outwit you. But otherwise, in theory, if you can get it in your body and go to step E, you're immune, if you can get to that point. Ebola, for example, will kill you in hours, so you're not good. If you live through Ebola, you'll never get it again. That's the concept. Yeah.
One final question.
Sure.
So, okay, so when the 1919 flu happened, what they said the young people were dying from was the cytokine storm because their bodies overproduced that. So that's in this step or part C.
There,
D. And so they just made too much of that, and then their bodies almost like got fluid in them because of it.
Yes, because the irony, their immune system was so good at responding, they responded so fast, it actually wiped them out. So that old people will live through it because their immune systems took so long to get going that nothing happened. The young people, old soldiers mostly, would ramp up on C and D so much that basically they wiped out all their energy reserves, they wiped out everything else in the body to fight the war.
Well, and I also read that the children that get hantavirus don't die from it because their immune system works so slowly because they don't have the storm.
Exactly right.
Okay.
Although you'll die of a regular flu, just not of the 1918 one.
Yeah.
Right, cytokine storm. We'll get to that actually next week. We do a cytokine storm.
So why can somebody say get chlamydia 10 times? Why can't your body just learn and protect against it?
In theory, your body can.
You just want to be crazy.
Well, yeah.
You have to explode.
One of the other tricks with a lot of STDs and stuff is they actually don't go inside the body per se. They hang out in mucosa and stuff, so they get a little bit more protection. Plus, there's multiple versions of chlamydia. So you may remember the first one you had, doesn't mean you're going to remember the next species you get. Right? So you could be immune to the one, and then also you got the immunocompromised. If you're doing all the bad stuff that gives you chlamydia, chances are you're under stress, and your immune system is shot anyway, so it doesn't matter. But there's multiple facets of that. Make sense? So where was I going? I just had a thought. Get rid of chlamydia. What it is. Anyway, what was I going to say?
I mean, I've worked with it every
You all.
It's not a pretty flower.
Oh yeah. So let's go through this picture here. That's what I was going to remember. PCC says, "Thou shalt memorize this table, thou shalt." All right? So we're going to make a table on the board up here. That is this table, just in a little nicer version. This is the IG table. So over here, we're going to make the IGs. All right. What this means in English are the antibody types. The fancy speak for antibody is immunoglobulin. That means antibody, and you abbreviate that word as an IG. So in English, IG means antibody. It just sounds expensive. So you'll notice that the different types all have letters. IgAs, IgDs, IgMs, IgGs. So you're supposed to memorize the different IGs. I'll put them in here alphabetically. So IgA, IgD, IgE, IgG, and IgM. These are different kinds of antibodies made by B cells over their need. You're supposed to know where they're found and what they do. So let's go through in order. IgA. Read that and tell me where you find IgAs.
Plasmas and saliva, tears.
Okay, how would you summarize saliva, tears?
Fluids.
Fluids, body fluids. On a test, you can say IgAs are secreted in body fluids. They're made in my B cells, but my B cells put them into the body fluids. They end up in my body fluids. All right? All right. So let's do IgDs. Where do you find the IgDs in your body? IgDs.
They're always with your B cell.
Attached to a B cell. That's the one that was at step A. That was the one that enabled the B cell to grab onto something. So IgAs are secreted in body fluids. IgDs stay on the B. IgEs, where are they found? Let's see, mucosa. Mucosa is a good word. Mucus or mucosa. So give me an example of mucosa in your body.
Your snot.
Snot, airway, right? Gastrointestinal tract, reproductive tract. So all the slimy parts, right? So IgG, where are they found? Plasma, blood plasma. So these ones are left in the blood plasma after the B cell thing. IgM, where are they found?
On the B cell?
On the B.
And plasma.
And plasma. So they sort of do a double one. So IgAs are found in body fluids. IgDs stay on the B. IgEs are found in mucosa linings. Gs are in the blood plasma. And Ms are found in Bs, and, on the Bs and in the plasma. All right, so we can summarize this. I came up with a stupid song. If you hate it, don't blame me. That helps me remember this for the last 20 years. So IgAs flow away. Name something that flows away from your body.
Fluid.
Tears, spit, semen, all that stuff. So IgAs can flow away. IgDs are on the B. IgE is allergy. Let's look at E. Let's look over here what it does. See a word in red? What's it say? Histamine leading to allergic response. So IgEs, we'll learn next week, responsible for allergy. Because where do you get allergies? In your airway, in your digestive system. So that response leads to allergy. IgAs can flow away. IgDs are on the B. IgE is allergy. IgG is bloody baby. Okay. Bloody tells me plasma. Baby tells me over here crosses placenta. Bloody baby. It's in the blood and can cross the placenta. Unfortunately, I can't come up with anything for IgM. IgM, I don't know. I'm a white guy. I can't come up with it. All right? But these are how I remember them. But you are to remember the letter, where they're found, and anything special, like, for example, allergies or E's. Make sense? Remember, find this table in Saladin and your lab manual. Let's find a new one. Take a picture of it. Whatever. But you need to know that chart. Immunoglobulin class. Yes? That would work. Nation. Just doesn't have that rhyme thing. Membrane-y. I don't know if that works.
Are we supposed to look up the functions?
They all have the same function. They're all going to stick to antigens,
Oh,
right?
okay.
The only difference is these ones are first, this one's on the surface. There's a little difference down here. They're all basically the same. So if you're a B cell and you're going to make an antibody that's going to cross to a baby, you're going to produce an IgG. That will go in the blood to the baby and do those things over there, mobilize and complement. Make sense?
Mm-hmm.
So thou shalt know this, thou shalt. So that ends kind of the B system. Now we have to learn the T system that's over here. So you're going to leave all the space. We're go back over this board because we're using the same steps as the B to make a T. Right. So let me show you a T cell so we can get our bearings here. Here's a picture showing a T cell at the bottom. Oh wow, I know this. That's that APC joke, right? Okay, but look what kind of T cell that is. What T cell is that one? Cytotoxic. That's different from the helper T cell. So you're going to use the helper T cell. And over here, we're going to start changing these letters to represent that T cell there. Over here, we're going to do T cell system. It's called cell mediated. Cell number. Okay, on that picture, that's a T cell attaching to what? It's not an antigen or a pathogen anymore. What is it attaching to? What is that? APC, or we can say a non-cell antigen. An APC, for example. So my T cell is going to stick to anything that's non-self, for example, the APC. And what do you do after you attach to something? Take a guess. You're going to wait. Wait for what? The helper T cell. Wait for orders. In the military, you don't even do anything without orders. So the helper, this is not a helper T cell. What kind of T cell is that? Cytotoxic. Cytotoxic T cell. Oh, sorry. Not that one. This one. Cytotoxic T cell. That's helper. Sorry, I raised the wrong one. The cytotoxic T cell will then proliferate because the helper T cell told it to clone. So it's still going to do A, B, C, and D.
Is this just sort of like a general T cell, and then it waits for the more specific T cells, the helper and the cytotoxic?
No, this one becomes a cytotoxic after it gets the orders from the helper T cell. This one and this one are the same. This
Okay, the helper activates it and it becomes this new
Yes.
thing. Okay.
So on a picture here, on the left-hand picture, here's my step A. I've found an antigen that's not me. I'm getting the orders from this helper T cell over here. And then I'm going to proliferate. And what am I going to make? Let's find out. What are all these things? Those are cytotoxic T cells. So when we make our clone, some of the clones become more. That's a bad pen. Some of them become cytotoxic T cells. They don't make antibodies. What do you think cytotoxic do? They kill cells. Let's find that picture. Hey, there they go. They're killing that cell up there. So they're going to kill all cells. Which cells are they going to kill? Not every cell in your body.
The infected ones.
Infect the ones with
The non-self-antigen.
Self-antigen. So if you are not me, I will kill you.
Are these specific to the original non-self
Yes.
antigen? Okay, so
They're exactly the same clone.
So they kill not just any non-self, but that non-self.
That non-self specifically. Yes.
Are the helper T cells activate the T cells with the cytokines as
Yes.
well?
Same thing.
Those infected cells are your own cells that have viruses.
They could be, or they could be
The virus,
something else.
bacteria or whatever, but they could be your own cells.
That's right. So in English, we did the same kind of steps to T cell. We turned them on. We made clones. In this case, the clones actually will kill. They don't make antibodies. They actually kill. But then guess what else we're going to make besides the cytotoxic T cells? What other ones could we make?
Memory.
The memory T cells. And why would you want a memory T cell?
To patrol around and look for them.
Remember for the next time. So again, I'm still going to do that memory thing. I'm learning to kill a specific shape. So, that vaguely gets...
So, the memory T cell, is that activated and then it creates clones of the cytotoxic T cell?
It would when it got activated the second time, yeah. So we make them, and the next time they act as kind of a D. They clone. So let's go back to our animation. Back here. So we did the same responses. The helper T cell got turned on. Same effects. Now we're going to do the
From
T
this
cell.
point follows two paths, one using cytotoxic T cells and one using B cells. Normal cells of the body that become infected can also digest some of the pathogens and display antigen fragments on their cell surfaces.
So here's some more non-self floating around. This is a different step than the APC step. We already did that step. This is another cell that's getting non-self, if that's even a verb. Right?
The body makes millions of different types of cytotoxic T cells. Each type is able to recognize a particular antigen. The cytotoxic T cells that are capable of recognizing the antigen displayed on the surfaces of infected cells bind to the infected cells and
well, not yet. They have to do what first? They have to get cloned, get the orders, and then they'd actually
produce chemicals that kill the infected cell. Death of the infected cells results in destruction of the pathogen. B cells also come in millions.
Right? So the idea is that we have to destroy the village to save it. That's the same analogy here. I killed the cell, that's you, but I kill what's inside of it as well. Okay? So T cells kill cells, B cells make antibodies. But between both of those, you should be able to trap and kill anything. Make sense? The next time you feel miserable with the flu, just realize it's your own body wrecking your lungs. That's what the flu is doing. The flu hides in your lung cells. Your T cells have to blow away your lung tissue to try to get to them. That's when you're coughing up some ugly-looking furball. Right? Not that I do. So, let me show you this picture here. This is going to run us through both systems side by side. So here we have the first exposure. Someone just sneezed on you. What do I have to do first? I have to turn on my helper T cell. So here's my macrophage, my APC. We eat and display the trophy. Now my helper T cell, the general, has the order. He understands. So what's he going to do? Or she? We're going to turn on B cells and T cells. Let's do B cells first. What do my B cells do when I stimulate them with my helper T cell? We're going to clone two kinds. Memory, which reserved, and plasma cells. What do plasma cells do?
Antibodies.
Antibodies. What do? They stick to you. Right? So landmines, flypaper, whatever you want to use the analogy. My cytotoxic T cells, I'm going to turn on. They're going to clone just like that. And some of them are going to kill things, and some of them are going to remember how to kill things. Right? And then the second time I get exposed, antigen second exposure, my memory B cells, memory T cells, and also there's some memory helpers, would respond quicker, faster, stronger. So I would kill the virus or whatever before it kills me. Makes sense? So you've learned to kill a specific shape. Makes sense? Adaptive and specific. Makes sense in the immune response? There's none. Alrighty. We got your packet of pain. We're going to put you to the test here. Find this page. Page 31. We're just going to do the first page. We're not going to do the second page. Alright, so I'm going to walk you through kind of together for some of these questions. But what you're going to do is, here's baby Joe, here's the lab work. Your job, future nursing professionals, is to look at this and try to figure out what's wrong with it. So let's go through it together. RBCs, are those okay? Yes, they are. How about his platelets? Are those okay? Yes, they are. How about his white blood cells? No. I don't think so, right? 3,500 is a lot less than that. So the doctor realizes you have a white blood cell problem or an immune response problem. Being a good doctor, the doctor then breaks down the white blood cells into their type to look at if it's specific or not. So neutrophils, are they okay? Yeah. Yes, they are. How about eosinophils? Yeah. Fine. Monocytes? Yeah. Cool. Basophils? Yeah. Fantastic. Lymphocytes? Not a chance. So what's that tell you is wrong with baby Joe? What part of his immune system is not working? Yeah, this one here, right? The specific adaptive defense. So he has the non-specific ones, He just lost the specific ones, right? Doctor's smart. Doctor then breaks down T's and B's. Are his T's and B's okay?
No.
No, they are not. If you look at the T's and B cells, they're very low compared to what he expects. So we've analyzed now that his T cells and B cells, or the innate specific responses, are low. Right? So which ones are the most abnormal in his body? You would say the B and T cells are the most abnormal in his body. Yes? We'll get there. Hold that thought. I'll answer that. Guaranteed. Okay, so we're going to skip down to the last question. All right, let's explain his symptoms. What were Baby Joe's symptoms up there? What do you see? Chronic infections all the time, right? And why is he, how does this explain that he's always getting sick? I don't remember, right? So if I catch it once, I'll catch it again. I can't remember it over and over. So you keep getting the same infection twice, 3 times, 4 times, 5 times. The fact that you're not sick all the time, thankfully, is because you remember it the first time. When school was at age, right? Right. So we figured out that he has symptoms because he no longer has specific adaptive immunity, or the B cell response. So let's leave question 3 then. We'll work up. Do you think he'll have a normal level of antibodies in his blood?
No.
No, why not? No B cells. B cells make antibodies. I have no B cells, I can't make antibodies in any real way. Right? So what would happen to you if you don't have antibodies? What's the job of antibodies?
They help hold things down for the rest
Hold
of the
things down to beat them up. So hence, if I get an infection, I have nothing to stop the infection from moving and spreading. Right? There's nothing to hold the infection down. Make sense? So we figured out he doesn't have T's, he doesn't have B's, and the B's, therefore, he has no antibodies. Make sense? Okay, so question 2. I have to change my gears here, so hold on. When you do question 2, you have to go back to the blood unit we did way back when, in the dark ages. You're supposed to remember where your blood cells come from. So let me show you this picture here. Goodness, where did I lose it? Here we go. Okay, PCC says you're supposed to understand this thing, but they don't tell me you have to memorize it. So I'm going to take it the easy way and say you just understand. Right? But let's start here. What is hemocytoblast in English? Stem cell where?
Blood.
Bone, right? Hemo, blood cell maker. That's in your bone marrow. It's a bone marrow cell. So if you look at this picture, your bone marrow cells make all these baby cells, call them anything. These baby cells give rise to those cells. Reds, whites, platelets, right? All blood comes from your bone. So here's the catch. Let's figure out the pathway. So each linear line is a different chemical cascade. So making reds is a different series of steps than making this white or these or these or these. So if you look at Baby Joe's data, which pathway or ways is the one not working? Let's go back to the picture. Are his reds okay?
Yeah.
Are his whites okay? Some of them, except for these 2. So he has a problem making his stem cells produce his lymphoblasts, which in turn makes lymphocytes. So he has all the other white blood cells. They're fine, but he doesn't have these 2 because of this process over here. Make sense? So it's a different pathway for each cell. So you can be high in one, low in the other. Why not? But why can't he make lymphocytes? Well, the answer goes back to his data. Go back up here. NK cells. See that line? Anyone know what an NK cell is? It's a lymphocyte. Natural killer. All right, but they're missing something on them. They do. They miss specificity, meaning they're not specific. How could a cell not be specific?
No,
it kills part of you and part of it.
True, but what would you see on the outside of a cell if it was not specific? Or what would you not see on the outside of a cell?
No antigen.
Let me show you a picture, since you've asked. No, you didn't ask, I did. Let me show you a picture of this. This is showing, without a screen, the outside of a B cell, or helper T, or actually a cytocine T. Remember that antigen thing where you have the stick? This is the antigen of your immune system. This is what would grab the invader. That's also called an antibody or an IgG. So if you look at this thing down here, you will see something you remember very well. What is that? That's this chromosome. In English, what's chromosome?
DNA.
Your DNA. If you remember Biology 112, and just nod because you're lying anyway, that DNA makes mRNA, and mRNA makes protein, right? This is the central dogma. So if you look at the colors, this is just you as trivia, your body takes your DNA and randomizes it to make different shapes here. Why would your body need to randomize your DNA for this shape?
Because bacteria mutates?
That's right. If I want to grab something that I don't know about, I have to make every possible grabber there could be. So in your body, you rearrange, they call it, your DNA. So these ends of the shape are always different from each other. So in theory, there's a B cell that could grab anything and a T cell that could grab anything. Make sense? Otherwise, you only grab one thing. Well, let's say that you have a mutation where this doesn't rearrange. What would you see on the outside of your cells if they can't make that?
Same grabber.
It wouldn't be specific, right? So what would they kill? They kill everything, but non-specifically. So when you call a cell that's missing this chain, go back to this baby Joe. What do you see? Those cells there that are non-specific. What does it tell you is wrong with baby Joe? His body cannot make the antigen receptors on the surface of the cell. Therefore, he doesn't make lymphocytes that remember anything. Right? So it takes shapes to remember. Make sense? That's never on a test. But the idea is, if I can't make the shapes, there's nothing to remember.
So he's not making more natural killer cells than normal. Those are the only ones that exist.
There's no ones that exist.
He can't make the other.
In theory, if you took the NK cells and put those on them, they'd be the other two. That's the logic behind it. They'd be the other BSTs. Make sense? So he has a problem with this ability to make different shapes on the surface of the cell. What are those trivia? Does anyone know what SCIDS at the top of the case study stands for? Up here. Future nursing professionals that you are. Severe combined immunodeficiency syndrome. This is the baby in the bubble. Remember the John Travolta movie?
Oh, yeah.
Don't watch that? Right. So these people have no immune system that remembers anything, so you would die every time you got exposed to the flu or whatever, because you don't remember the shapes. Right? This is the concept of that. Just for, yeah, go ahead.
Is that a permanent condition?
Yes. Because you're genetically, there's a gene therapy they tried, it seemed to work, but it's, to my knowledge, it's forever.
Can people live very long with this?
Not normally, no. Just the bubble idea was to get you to your teens. That was the bubble idea. So the worthless trivia, look at the lymph nodes in the second paragraph. What does it say about the lymph nodes? Why are they not inflamed? He's sick. No lymphocytes, right? I mean, they're not there to do their job. The NKs are. Therefore, he's not going to get the specific defenses of the lymphocytes. So you with trivia. But there's a problem making your specific adaptive immunity. So you can't remember any sickness, therefore you're always sick all the time. That's the idea here. Cool? Yes? Good. So questions on B cells and T cells? I can feel your brains dripping out of your ears. Okay, so next week we'll finish up immunity. I think we're on track. Have our lab exam next week, final in 2 weeks. Vote early, vote often. Not here.
Quiz or exam?
The lab exam. Yeah, the lecture quiz. Your final exam
He's not like your typical
I know which one, right?
I mean, I get like other
You know, actually, when you go to one of the mentions after this train, the mention, yeah, all your information, when training the mention, the audience can ask them. To answer the question, you have to understand everything.
This is a page or should be me. I've never written my name. And you want to take it after next week or before Friday?
Did you send me this one on the email?
Before the... I think you want to do is one with the mail Friday, Friday,